You have for me chapter 1, section 8, please. Okay. Because I said that it was equally possible to examine our entire procedures through both the realm of starting from propositional logic and the realm of starting from sets, I should be able to do set operations the way I did logical operations. So let's define operations on two sets. We already defined the operation on one set, right? We looked at the complement. Well, a set complement. Wait, as soon as I said that, I realized I might not have actually said that in this class. So we'll do all of them. Let's start with a set and its complement. The complement of a set.
I was asking, are we officially on chapter 2 now?
We were as of Monday.
As of Monday.
Yes.
Okay.
All of chapter 1 ended with logic. All of chapter 2 starts with set. The complement of a set, a complement. Usually written A with a bar over it in this textbook. My other textbook uses a superscript C for complement. I have another textbook that uses a prime. I'm going to define this in terms of logic. Okay, wait a minute. I wrote it in set builder notation, but this is a logical idea here. A bar, the complement of A, is the set of elements X in my universe. What's that symbol mean? Not in, not belonging to, not an element of A. This is the set version of the not command. Okay. We did English letters, didn't we? The set of letters in English. And then I had this set V of vowels.
Yeah. Circle.
Right. So V is a set in this universe, right? Well, then V complement, it's a bar, not an arrow, sorry. I got caught up in vectors, wrong class. V complement is everything outside. All the letters that are not vowels. Wait a minute, we have a name for that set. What do we call the letters that aren't vowels? Presto. So I have this idea of negation, of not. And since not was a logical idea, I can now define not as a set idea. But I used the logic idea to define the set idea. We are allowed to go the other way. You can use the set idea to describe the logic idea, because remember, we said the set of things that make a proposition true, that's its truth set. So the negation would be the complement of that set. Not was our only unary operator. It was the only thing that worked on one proposition, so it would be the only thing that worked on one set. Questions? Yes, sir. Consonants. So what were our next logical operators? Oh, and or. I can only do the and or of propositions that are in the same universe, the same type of discussion. I can't talk about a propositional function about people and a different propositional function about numbers and then kind of glue the two together. It doesn't really work. So I need these two sets to live in the same universe. Then I can define two new sets from these. The set of elements where X is in A and X is in B. And I can define the set of X such that X is in A or X is in B. Exactly the same idea. I'm going to call the and one the intersection. And I'm going to call the or one the union. The symbol for intersection is a rounded version of the and symbol. The symbol for union is a rounded version of the symbol for or. I always remember it as the U in union and the N in and. But they match our other symbols, the wedge and the V, the same way. We make a Venn diagram here. I've got two sets in the same universe, means my Venn diagram is going to have two circles in it. I'll label the one on the left A and the one on the right B. Which do you want to do first, union or intersection? So the intersection requires me to be part of A and part of B at the same time. That's this piece. The overlap between the two. Whereas the union is all of it. All of A, all of B, and everything in the middle. Here are two sets living in the universe of integers. Although since I gave them as explicit listing, it really doesn't matter. Set A is the numbers 1, 3, 5, 7, 9. Set B is the numbers 1, 2, 3, 4. Give me the union, give me the intersection. That?
The intersection is.
Aha. I need to be in both at the same time. Yes, no, yes. No, 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 no. There we go. And then the union would include 2 and 4 from here with everything that's already in here. Remember, in our definition of a set, it was unordered. I don't care what order you put the numbers in. Questions? Yes, sir.
What would like an example problem would you do for this one?
Well, I mean, I could give you a bunch of sets and say, give me a union, give me an intersection, give me, yeah, all sorts of stuff. Oh, yeah, that's one of the easiest ones, but we'll do more in the same vein as we did with the logic ideas. Because again, this was only 2, right? I started with P and Q, but then I had R and S and all these. It's coming. Other questions? These 2 sets had elements in common. The intersection was non-empty. If the intersection of my 2 sets is empty, then those 2 sets are called disjoint sets. What's the Venn diagram look like if my sets are disjoint?
2 circles not touching.
They're completely unoverlapping. But let's start counting things. Remember, that absolute value here means cardinality. It means the number of things. So let me go back to that union picture. I want to count things. You've got this example right here, right? How many things are in the union? How would I, even if I didn't know the sets, how would I count the things that are in the union? I could count all the stuff in the first pile. Set A. I could count all the things in the second pile. So I could start by saying, let's count all the things in set A, and then we'll add on all the things that are in set B. If I do that with the example that's at the top of the screen, I get the wrong answer. Why? I have repetition. 1 and 3 are repeated. Because they're in the intersection. They got counted when I counted set A. They got counted again when I counted set B. Visually, I can say, oh, I counted this bit twice. Well, if you count it twice, but you only wanted to count it once, you should subtract it off to remove that double counting. To remove the repetition, I need to remove anything I double counted. You included it twice, that means you need to exclude it once. This is called the principle of inclusion and exclusion. If my sets are disjoint, how does this change? Exactly. I wouldn't need to subtract anything because this would be a 0. If there's no overlap, the intersection is empty, the size of the empty set has 0 elements. So I get A, size of A plus size of B minus 0. I don't need to worry about it. There is often a separate version of the rule given to that says if the sets are disjoint, then this. And my reaction is no, don't bother to memorize a new rule. Just remember that disjoint means there's no overlap. Subtract a zero. More questions? Talk to me.
The vertical lines.
A cardinality, number of distinct things in a set. Some textbooks use n for number, so we would write number of things in A. And some older textbooks use the number sign the same way. But it's just how many things are there and how many different things. So that takes care of repetitions. More questions? I got one more set operation for you. The set difference, A minus B. Sometimes it's written as a backslash instead of a subtraction symbol. Either way, this means I'm in A and not in B. If I were to ask you to shade the part of the Venn diagram that represented a set difference, what would you get? Ian?
So it would be A, but not.
A, but not the intersection. I have to take that bite out of the cookie. So I'm not allowed to use the pieces that are in B. Which means, in the example that is now off the top of the screen, with those two sets of numbers, what's the set difference here? A take away B. Everything in here, pull out those. Questions, comments, other weird things you want to ask about, talk to me.
If this is a repetition, would you just take out one of the ones and one of the threes if you were counting how many things were in that? So those A and B have 1 and 3. If you were counting how many objects are in A minus B, would you get rid of the repetition or the whole number entirely?
There is no repetition. Let's actually put these sets in a Venn diagram. So I have the universe of integers. My set A consists of the numbers 1, 3, 5, 7, and 9. My set B consists of the numbers 1, 3, 2, and 4. There's no repetition. You sneaky mother. Roman, this is another thing that often gets asked. Here are some things about sets and their intersections, their unions make a Venn diagram. we had back on page 27, 28, a bunch of identities about logical things, right? De Morgan's rules, the distributive rules. Remember all of those and how much fun they were? Here they are again. It's the exact same rules written in terms of sets. The very first rule we had said P and true was the same as P. A and everything is A. It's the same rule. The truth set of the true statement is everything. A or the empty set. You need to be a member of A or you need to be a member of the empty set. There's nothing here to add on, it's just A. It's the same rules. I just changed the language they're written in. All of them. Our double negative rule. Not P is P. Complement of the complement is the original set. Hey, look. De Morgan's rules. Not A and B is not A or not B. The same blankety blank rule. I could prove all of the rules that we did with truth tables with set ideas. The exact same way. So, page 136 is where that giant list is. But let me just pick one. A and B or C. In logic terms, we distributed and we said this was A and B or A and C. I mean, if I go back to page 26, I will see this. The same sentence. So, how do I prove one of these things is true? How do I check this? The way we were checking stuff back in logic. Like do it in two different ways.
You could do the counter, I've written that enough times I should be able to say it,
Contra positive thingy?
yeah, counter positive.
I think that might be a lot more trouble than it's worth, but yes, I should. The problem is writing a proof in sets is hard. To show that I have two sets that are equal, I really have to prove two different things. I really have to show that everything in set one is also in set two. In other words, that set one is a subset of S2. So everything in S1 is also in S2. But then I have to show it the other way around. Everything in set two is also in set one. So every proof, it's very much like an if and only if proof. I have to show two different things. This does not sound like fun. Let me give you an example so you can see why I'm not thrilled with this idea. Let's do De Morgan's law. Not A or B is not A and not B. So this is set one, this is set two. I'm going to do two proofs. One, show A union B complement is A complement intersect B complement. This is a direct proof, Emily. I don't have to do a single contraposition here. I'm going to suppose we have something in that first set and end up showing it's also in the second set. Directly. Proof. Let X belong to A union B complement. But that means that X is not part of A or B. Well, if it's not part of A or B, then it's not part of A. At the same time, if it's not in A or B, it's not in B. What conjunction should go between those two words? It's not in A, it's not in B, and. But wait a minute. X not in A, that means that X is in the complement of A. Not in B means it is in the complement of B and intersection. I started here, I ended here. Check mark, part one. Well, that took a bunch of braining around, didn't it? That was just a load of fun. I got to go the other way now. So now I have to start down here and work this in reverse, right? For part two, I have to show that A bar intersect B bar is contained in A union B bar. Got to show the containment the other way. So now I start with something in here. Let X be in A complement intersect B complement. I'm literally going to write these sentences in reverse order because that's exactly the thing that's going to give me what I want. If it's not in this and that, that means that X is in A complement and X is in B complement. And that means X is not in A. Wait a minute, X is not in A. This means X is not in B, but I've taken the negation of a logical sentence. When I negate a logical, what happens to the conjunction in the middle? Flips over. Oh, there should be a bar on this one. Got to write the right stuff, people. Catch me at it. Well, if it's not in A or it's not in B, then X is not in A or B. And that means that X is part of the complement, which is what I wanted. Wasn't that just the most fun we've had all day? No. This is horrible. I don't like doing this. When we did logic stuff, we could show that two logical expressions were equal by this sort of idea, right? What else could we do? I could do a truth table. truth table for set. I said it earlier. The truth set is the set of elements that make a proposition true, right? So I can think of being in as a true and being not in as a false. Instead of thinking this is a truth table, I'll think of it as a membership table. You're a member of set A, true. You're a member of set B. Instead of using trues and falses, let's use ones and zeros. So when you are a member of a set, I'll write down a 1. When you're not a member of a set, I'll write down a 0. So I have 2 sets, A and B. Well, I could either be a member or not be a member. How many options do I have total? I have 2 for A. I also have 2 for B, right? So I could be part of A and part of B, or I could be part of A and not part of B. I could be not part of A and part of B, or I could not be in either of them. Hey, wait a second. Wait a second. Go back and look at the Venn diagram with 2 circles in it. I'm going to label each of the parts of this Venn diagram using that code. I'm not in A, I'm not in B. That means I'm out here. I'm in A, but I'm not in B. I'm in B, but not A, and I'm in both. 4 different places I could be, 4 different options. But now, I can make the left-hand side of my argument, and I can make the right-hand side of my argument. Remember what we were trying to show, as I pull back up the previous page, was this. So I'm going to make this, and I'm going to make this. And then I'll compare those 2 columns, just like we compared the column of trues and falses in our truth table. So A union B, then complement. A union B. Union means or. Like or is true, 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 false, 1, 1, 1, 0. The complement becomes yes, sir. Means not in. So it's the opposite of being in is being out. That's the left-hand side here. So I put a little star on that. That's one of the one of the columns I want to keep track of. Now I do the other side, which was A complement and B complement. So let's make the A complement column. What's that? And B complement. And now and. That's the other side. Hey, they match. They have exactly the same sets members. The union AB would be everything inside either circle. I take the complement, I'm outside. That's the 0, 0 label, isn't it? A complement would be everything outside this circle. B complement would be everything outside this circle. The overlap of those is the 0, 0 region. I prefer membership tables to doing this. But I like truth tables. If you hate truth tables, you may very well prefer this to membership tables. It's your call. Questions?
Say the A and B with the line we're talking, I can say they're separate.
A complement, intersect, B complement. So it's kind of like not comes before and or. So if you're not P and not Q, kind of like that, like kind of parentheses in my voice by pausing just right. Really wish I could speak in punctuation, but no. That's Victor Borgia. There's a really cool video on that, and it's funny as hell. So that's my version of reading that, is just to pause at the right places, Dan. Does that make sense? Okay. More questions? My preference, again, and it is just a preference, is to do a membership table over a set argument. You'll notice what I didn't do. I didn't just draw a Venn diagram for each side. Because I have to show that what you've drawn is actually the correct Venn diagram. And that would really be a series of Venn diagrams to do each side, wouldn't I? I'd have to draw everything outside of A, the complement of A. I'd have to draw everything outside the complement of B, and then I have to intersect those, so I really need 3 pictures just to do that side. And then I need 2 more pictures to the other side, and I'd say, oh, look, the final picture in each one is the same. That's a lot of drawing. And as these get longer and more complicated, more and more Venn diagrams come out, and larger Venn diagrams are hard. What if I have 3 sets? I got a lot more pieces here, don't I? Here's a question for you. Do I have all the pieces I can make out of 3 sets?
I think you would have like B, C, A, C, and A, B.
Okay, but you haven't given me an operation for those. Is that union or intersection?
Intersection.
So A intersect B would be this lens shape right here. Yes? And this one, what's this one?
C.
And that means this one over here, that one is A intersect C. Yeah, what's that? Seth? So it turns out I've got 3 options, right? I could be part of A, I could be part of B, I could be part of C. Think about the truth table. The truth table would have 3 things, right? And then I would have 8 options. 1, 2, 3, 4, 5, 6, 7, 8. I have them all. If I want to add a 4th set, my 4th set needs to be part of every one of the 8 options here. It needs to take every one of those 8 things and split them in half. Because I'll need 16 total options, right? Oh, crap. You cannot make a Venn diagram for 4 sets using circles. Because I can't just put another circle somewhere. It'll miss one of these small intersections. So what I need to do is I need to make my 4th set kind of weave back and forth a little. I did not make the following picture. I stole this from online. My 4th set is that upside down C shape. But notice that it crosses all of the other bits. And I went ahead and, like a psycho, labeled all the bits, because I'm nuts like that. On our web links section on our Canvas page is a link to a paper about Venn diagrams. Whole web page with all sorts of Venn diagrams. That's where I stole this from. It turns out you could use the same shape every time. But if you want to use the same shape every time, that shape can't be a circle. It turns out to kind of look like a wing. It's got a round part and it's got some fingers that stick out the side. It's very weird looking. It's on that page. But the more sets you get, the weirder these suckers look. My 5th set is woven back and forth around the boundary edge of the 4th one. It's not worth it. On the other hand, the web page that I've linked you to on the Canvas page is all about combinatorics and gives us lots of different pictures of Venn diagrams. Am I ever going to make you try and draw a picture with more than 3 sets? Nope. It's possible. You can draw all sorts of very pretty mandala style drawings with more and more sets. But for the most part, I'm going to think of these symbolically. And so that means I can think of the intersection of a lot of sets, right? I could think of A1 intersect A2 intersect as many as I want. Yes? I could intersect 17 sets or 35 of them. Wait a minute. A and B and C and D and... Didn't we write a shorthand for that? Was a giant and symbol? There's my loop. Take the intersection, A1, intersect with A2, intersect with A3. Just keep counting from 1 to N. You want a union? Do it the same way. I think of these as indices, right? I've got an index telling my set apart. One of the things that happens down the line in set theory is the idea of indexing infinitely many sets. Remember, cardinality tells me how many things we've got. So if I have n sets, n is some number, 17, 32, 112, 6,000, 65,536 of them. However many sets I need, right? But what if I need more? I could try and think about the idea of taking an infinite pile of sets and gluing them all together as a giant union. Or intersecting and just keep intersecting. Keep going, man. We'll be here forever. Yes. Are there places where that is necessary? For this class, no. But in general, in higher mathematics, yes. There's a lot of very interesting questions about infinite collections and infinite sets in particular. Usually when we write an index set like that, we will have the union where I is my index set, AI. Up here, the set I was just the numbers from 1 to n, but this I could be any set. So you have phone numbers. I'm assuming most of you have more than one. Listed on your record here at the institution, you have your personal cell phone, but you also probably have your parents' home phone, or your home phone if you still have such a thing. I know most people don't bother to have a home phone anymore. But if you've got somebody else on your record here, maybe you've got your spouse or your partner's phone listed as your emergency contact. So it's quite possible that the set of phone numbers associated to you is not just one number. So I could take the union of all of those sets, couldn't I? I could do it for every person on campus. That would be a bigger index set. My index set would be the entire registrar database. I could do it for every person on the planet. I'd be here a long time. I could ask for the intersection. Let me do it the other way. Not just the numbers that are listed for you. What is in your phone book? Pull out your contact sheet on your phone right now. That's not a short list, is it? I'll bet some of you have phone numbers in common. If I took the intersection of all of the phone numbers that you put into your phones, would I get anybody? I don't know. How many of you put my phone number into your phones? My office phone number. Because it's on the syllabus, right? In case you need to call me, Dr. Sadler, I'm full flat, I'm 30, I won't be in class. I don't know. Maybe you all have a friend in common. Maybe you have a coach in common. Maybe there's somebody's phone number that's on every phone here. I don't know. But I could take the intersection using my index set to be the students' phones in this class.
I was gonna say, most phones nowadays do the emergency contact and then immediately goes to 911.
Ah, but that's actually a pre-programmed number on the emergency on the home screen, right? Because if I pull up my phone and it's locked and I turn it on, emergency is a separate listing, isn't it? And that connects to the 911 system in my area. What if I'm in the middle of nowhere? I'm between Kansas City and Tulsa, driving down I-70, whatever that is. I'm in trouble. So it does depend on whether you think of that as a common number, because it really isn't the same number. It's short. More questions? There's more to do with sets. But I'm not going to do that on Friday, because on Friday, we're going to take our test. Now, there are enough of you in this room that everybody get their own table for the test. So on Friday, one person to a table, ideally all on the right or all on the left. We'll figure it out when we get here, but everybody gets their own table on Friday. I will see you all then. Remember, you are entitled to a formula sheet. If you got an email from me earlier about coming to talk to me at the end of class, come to talk to me. Brandon, you got a question? In about another 5 minutes, along with the homework key for today's homework. So you'll have all of it to study from. Other questions? If I emailed you earlier, please come talk to me.